I'll begin with a word of prayer here. Heavenly Father, we thank you for this day. Again, I thank you for this class and this time we have to study your creation. Help us to glorify you when we do, Lord. In your name I pray, Lord Jesus. Amen. Here is the attendance sheet before I forget. I'll let you guys add a date to it, preferably today's date. So we were beginning to look at how to solve the homogeneous problem, right? So our goal at the moment is to find solution set for, L of y equals to 0, where L is equal to, let's say, an d to the n plus dot 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 plus like a2d squared plus a1d plus a sub 0, where an all the way on a0 are continuous on some domain of definition, right? And to be clear, we are trying to find a real solution set. So we are, if we find our way to complex solutions, that's lovely, but we do need to extract real solutions from those, all right? So that's what we're up against. And I showed you a method last time, right? And so basically last time, what did we learn? We saw that if you had down through a sub 0 elements of R, then if we look at the polynomial and the differentiation operator acting on e to the lambda x, we just get p of lambda e to the lambda x, right? Here I'm assuming that d is d dx, right? And so what that meant then is that if we're up against, if we happen to have the case that the differential equation is defined by a polynomial and the differentiation operator, then all we have to do is do what? We can just look at, so then basically for L equal to P of D, we can find solutions from P of lambda equals to 0, right? Because if you have P of lambda is equal to 0, that implies that L of e to the lambda x equals P of lambda e to the lambda x, which is equal to 0. So each distinct eigenvalue oh no, that's the eigenvalue. I meant each oh goodness. Each solution to P of lambda equal to 0 gives us a solution to the problem, right? And so if we have distinct zeros to the polynomial, great, we can just write down those solutions. But we haven't yet figured out what to do in the case that the root is repeated, right? Like if we had a repeated repeated value for the, so this right here is called the characteristic equation. Characteristic equation. Notice that there's no determinant this time, right? It's just, we just write down the same equation as the problem. Let me refresh your memory. Excuse me. With a couple examples. So example 1, we might have y prime 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 plus 3y prime prime plus 3y prime plus y equals to 0. We write down the characteristic equation, lambda cubed plus 3 lambda squared plus 3 lambda plus 1 equal to 0. All right. Then we factor. In this case, we have lambda plus 1 cubed equals to 0. So I only get 1 0, right? I get lambda equals to minus 1, you know, with a multiplicity of multiplicity 3, right? But remember the theory says that this is a third order differential equation, so obviously we're missing something, right? So all this gives us so far is y1 equal to something like, you know, e to the minus x, because lambda equals to minus 1 here. So I got one solution, but I need 3, right? Because the general solution should be a linear combination of 3 solutions. Where do I get the other 2? Is the question that we need to answer. Another example before I answer that question. We could have y prime 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 plus 2 y prime prime plus y equals to 0. And here I'll let y prime be dy dt. All right. So then what? Write down the characteristic equation. What is it? What's that? Lambda to the fourth plus lambda squared plus 1, right? If you want to think about it, the power of lambda we write down is the order of the derivative. If there is no derivative, the order of the derivative is 0. That's why we write down a 1 last, and not a lambda. Can you factor that? I can. This is lambda squared plus 1 squared. That's what that is. So this is a complex problem, right? So here we get lambda equal to plus or minus I twice. So what solutions do I get from that? Well, I get a complex solution, you see? I get a complex solution. So I get y equals to e to the ix as a solution. But what does that mean? Oh, did I say x? But what did I say up here? T, so take off half my points, right? So put a t there, and as such we use cosine t plus I sine t. This is Euler's formula, right? That's what an imaginary exponential does. It gives you a cosine and a sine, like so. And great, so if we look at it, if we say L is equal to, you know, d to the fourth plus 2d squared plus 1, that's the defining operator for this differential equation, right? And each one of these is a linear operator. And if I look at L acting on cosine t plus I sine t, what do I get? Well, I get L acting on cosine t plus I times L acting on sine t, right? But it's still equal to L acting on, I mean, overall, in summary, it's L acting on e to the it, which we know is 0 from the arguments which I've presented to you in the last hour or so. So we know that's 0. So what does that say about cosine and sine separately? Notice that L is a real differential operator, right? So this is a complex equation. It gives you 2 real equations, namely that this has to be equal to that. And if you use your imagination, you can see there's plus I times 0 over here, right? And this must be equal to that. So I get 2 real solutions from this one complex solution. This hopefully is familiar to you from the previous story arc in the course, right? So we get like y1 equals to cosine t and y2 equals to sine t solutions to L of y equals to 0. Is that enough to form the general solution? It is not. Right? What are we missing? 2 more solutions, right? All right, so let's get to it. How do we find these missing solutions? How do we find these? So I'm going to start down a discussion of operator calculus for you guys. And we'll start at the beginning. So this is my section 3.2, and I'm not going to follow it directly, but so first of all, like definition, how do we multiply operators? If I've got L1 and L2 are linear operators, then we define L1, L2 is a new operator defined by L1, L2 acting on F, all right, is L1 of L2 acting on F. So operator multiplication is understood in terms of composition. So for another example, if I had T as a different operator and I was talking about its cube, like T cubed on F, what would that mean? What's its meaning? It's T acting on T of F. So this is what we mean by like a power of an operator. It's understood in terms of successive operation. Let's actually work a calculation. Let's work an example here. I want to show you one of the dangers of operators. So let's let L1 acting on F be something simple like differentiation, df dx. And we'll let L2 acting on F be just multiplication by x. So, so this is multiplication by x. So I might even write this as xf perhaps, if that was, you could write it that way perhaps. I could be more obnoxious. Here, let me show you the completely mathematically rigorous but pedantic way of writing this. I could say L1 of f as a function of x is equal to df dx of x. There you go. Do you feel enlightened? L2 of f at x is equal to x times f of x. There you go. That's precisely what's meant by those black equations above. So let's calculate L1, L2 and L2, L1. Let's see what happens. All right. So we're gonna look at L1, L2, and we're gonna look at L2, L1. So what's L1, L2? And when we multiply by f, act on f here, what do we get? We get L1 of L2 of f, but L2 of f was x times f, right? But L1 was what? d dx of xf, right? What is the derivative of x times f? This is a what? This is a product rule. So what you have here is dx dx, which is 1. So I get f plus x times df dx. On the other hand, if I do L2, L1, what happens? I get L2 acting on L1 of x, which was df dx, right? And so that ends up just being x times df dx. So L1, L2, and L2, L1, they're related, but they're not the same, are they? They're not the same. See that? So if we would calculate what's called the commutator, which is L1 comma L2, by definition this is L1 L2 minus L2 L1. You can see that what you get from this is just 1. Well, I'm gonna write this here and I'll explain it elsewhere. I'll explain it up here. So like the commutator of L1 L2 acting on F is equal to, I'll see here, L1 L2, which was F plus x df dx, and then minus the L2 L1 acting on F, which was x df dx. So those pieces cancel, and it just leaves you F. But in this situation, if you've got L1 L2 acting on F, it gives you F, and this is true for all functions. Excuse me. If you have something's true for all functions, that means what you have is an operator identity. And in this case, the operator identity is that the commutator of, well, let's see, x was, L1 is ddx, right? So the commutator of ddx and the x operator is just equal to 1. All right. So operators don't have to commute. Like the commutator is 0. What that means is that the operators commute. If it's non-zero, they don't. Now this is not something we need to talk about extensively in here. This is just kind of a cautionary tale on the way to what we're learning here. But it is important to notice that operators don't have to commute, and that matters when they don't. And there's a physical meaning to this. Does anybody know what it is? So if you study quantum mechanics, it turns out that essentially momentum is represented by the differentiation operator, whereas multiplication by x is a representation of the position operator. And there's a theorem in quantum mechanics which says if you have two observables and their commutator is non-zero, what that means is that those physical variables cannot be simultaneously measured. And so this commutator being non-zero actually is indicative of what's called Heisenberg's uncertainty principle for position and momentum, namely that you can't precisely measure both momentum and position in a quantum state at the same time. So, because quantum mechanics is largely represented by differential operators acting on state space. So this operator calculus does have a deep physical meaning if you continue in that direction. But anyway, we don't need all that for here. So example, okay, so that's my example 3. We want to state kind of an easy theorem. If L is equal to L1, L2, ln, all right? Well, not even ln, let's say Lk, right? Where where L sub j is a linear differential operator, right? And if L1, L2, Lk all commute with each other, all right, then if L sub j of y is equal to 0 for any j in in this set of values, then L of y is equal to 0. So let's work this out. So let's, assume Lj of y equals to 0 for some 1 less than or equal to j less than or equal to k, all right? And then you look at L of y, which by assumption here is L1, L2, there's j in here somewhere, all that acting on y equals, right? So if the operators all commute, what can I do? If they commute, then I can switch the order and I can move j all the way over to here. See, I can rewrite this, assuming that they commute. I can rewrite it as L1, L2, dot, 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 Lk, and put the Lj over here, right? Assuming, yep, they commute. Thank you. Math major, you are in thirst of your, I have failed to put my marker like a dog on a fire hydrant. There it is. I'm sorry, that was unpleasant. Why do you guys hate dogs? But so yeah, I'll stop. So whatever comes past that, you don't want to hear. But then by definition, what is this? Well, this is, this operator L1, L2, da da da, Lk, that operator, and then we feed it Lj of y. Right? That's the definition of multiplication of operators. It's this composition, right? But what is Lj of y? Well, we've assumed it's what? It's 0. So this is 0. Something I suppose I should have taught you guys, and I failed probably, but if t is a linear operator, right? What's t of 0? It's t of 0 plus 0, right? If t is linear, is 0 plus 0 0? Surely you don't disagree, right?
I do.
You do? Get out. All right, so so if t is, if truth is relative, well, if truth is relative, that's just evidence of God's wrath on our country. So, I mean, it is. That's Romans 1. You want evidence of God's wrath? Look around. So, t of 0 plus t of 0, by assuming t is linear, what does this mean? So, for a linear operator, we have t of 0 is equal to 0. This is a basic truth about linear operators, right? So if I have a linear differential operator, these are all linear differential operators. Another fun theorem I should mention to you is that this is linear operator. So I'm not going to prove this in here because, we don't want to prove everything. But you can prove that the composition of linear operators is, again, a linear operator. If you'd like to see the proof, come take Math 321 with me. But it's not particularly deep. It's easy to prove. But this is a linear operator. This is 0. What happens when you feed 0 to a linear operator? You get 0. Hooray. So what does this all mean? This means that if we have a problem, right, and it can be written as a product of linear operators, we can, if those are commuting operators, we can solve each one separately. We can find the solution for each of the L1, find the solution set for L1, find the solution set for L2, find the solution set for Lk, and we can take those and combine them, and it's going to be a solution set for the whole thing. So this means that we can divide and conquer, basically. All right, so let me go on here. So let's think about something here. If if L is equal to a polynomial in the differentiation operator, right? And if you have, let's say, P of, we'll say P of x is equal to, like, an x to the n plus dot 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 plus a2x squared plus a1x plus a0, and let's suppose that factors as an times d minus lambda 1 to the m1 power, d minus lambda 2 to the m2 power, dot dot dot, d minus lambda k to the mk power. So suppose that you have a factorization of your nth order polynomial into a product of linear factors repeated like this, right? Then L is equal to L1, L2, dot 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 dot, Lk, where, and I guess I should throw a, I don't know, I need to stick the stupid an somewhere in here. This is very distasteful, this an. I usually set it equal to 1, but I'll, just for the sake of annoying, messing up my pattern, L1 is an d minus lambda 1 to the m1, but then past that, L sub j is simply d minus lambda j to the mj, for j equals to 2 all the way out to k. So what I'm saying is, if your operator is a polynomial in the differentiation operator, right? Then if that polynomial factors, like so, doodle-doo, then you can write L as a product of operators in the same way. And Li, Lj is equal to Lj, Li for all I and j. In other words, they commute. Which means that I can solve my problem using the method I just outlined in the previous theorem. Instead of solving the whole thing all at once, it suffices to figure out what the solution set is for each one of these factors, one at a time. I can figure those out. And if I can figure those out, then I can string it all together using the theory here. Now, this is a theorem which I have proved in past years, and we could prove again, but instead of proving it, I'm just going to give you an example of what I mean by this. The proof is pretty straightforward, actually, but here's an example of it. So you could accuse me of proof by example if you like, but anyway, where was I? Example 4? 5? 4? All right. For instance, if I have, I don't know, d to the fifth minus 6 d to the fourth plus 9 d, I can rewrite this as d times d to the fourth. Oh man, just a second here, I'll get it eventually. I wanted to put a cube here, I think, yeah. So if I factor out a cube from that, that gives me d squared minus 6d plus 9, I think. And actually the way this works is the differentiation operator actually allows you to factor just like this. This is d cubed, d minus 3 squared, like that. So this would be like my L1, and this would be like my L2. in the theorem above. So if this is L, what I'm claiming, guys, is that I can solve L of y equals to 0 by looking at L of d cubed, by trying instead to solve d cubed y equals to 0 and solving d minus 3 squared y equals to 0. See, if I can solve these two problems separately, then I can know from this theorem that any solution to one or the other of those, d cubed or the d minus 3 squared problem, will be solutions to the original fifth order problem. Now the d cubed y equal to 0 problem, you guys should be able to solve that since Calc 1. What is the solution there? What is this? This is the third derivative of y. I guess I need to tell you what d is. You want d dt? What do you want here? D equals what? You want x, t? X, t, I give you a theta. And there you go. Let's get weird. So d d theta. So d cubed y d theta cubed. What would the solution be? Like you got what? C1 plus C2 theta plus C2 theta squared, right? Well, anyway, I don't have room. So y1 equal to 1, y2 equal to theta, y3 equals to theta squared. These are three solutions to that problem, right? You take the third derivative of any of those with respect to theta, you get 0. But we need 5 solutions for this problem. Where are the other 2? Well, apparently they're from this guy down here, right? This, we know that we could find a fourth solution, e to the 3 theta, right? By what we were talking about last class, because that's well, maybe we don't know that yet. Excuse me, guys. All right, so now that we have this, let me carefully and methodically derive the solution. So, I mean, if you put everything together here, what we need to do is simply solve the problem d minus lambda to the m power equal to 0. What's the solution set to that? Once we work that out, we can solve anything with constant coefficients. So let's do it. I need a spot to do it. This looks like a good spot. And to do this, we're actually going to go back to the first part of the course. So here we go. So this is my, I'll just state it as a theorem. D minus lambda to the m power acting on y equals to 0 has solution set y1 equals to e to the lambda x, y2 is x e to the lambda x, dot dot dot, ym equals x to the m minus 1 e to the lambda x. So here, d, I'm saying d is d dx here, okay? Now rather than just prove, I could just prove it coldly. I could show you differentiation makes it work. But let me actually derive this a bit. So if we start with d minus lambda, acting on y equals to 0, what's that problem? This says that dy dx, right, is lambda y. How do you solve that? Separation of variables. We got dy over y is lambda dx. Integrate that thing, and we get that y is equal to like c1 e to the lambda x, right? So we'll just say y1 is equal to e to the lambda x because I'm not trying to I'm not trying to derive the general solution right now. I'm just trying to provide you a set of linearly independent solutions. Is there a question? No? No? Okay. So that's the one. So that's the m equals 0 case. Well, excuse me, m equals 1, right? The m equals 1 case. Just one solution. What's up next? So how about d minus lambda squared acting on y equals to 0? How should we solve that? Let me suggest we make a substitution. This is a new idea. So we've got d minus lambda acting on d minus lambda acting on y equals to 0. Well, if we make this equal to z, then you see what we have is d minus lambda acting on z equals to 0. Can we solve that? Yes, we can, right? We know how to solve this. This says z is equal to like c1 e to the lambda x. So then what are we up against? Well, as we said, d minus lambda acting on y is equal to z, but that's c1 e to the lambda x. Can we solve that? Well, I hate to erase all this. Well, guys, just write in your notebook, if you will, that we'd also get from what we're doing y3 is t cos t and y4 is t sine t here. And this is from y equals to t e to the it. So like this theorem applied in the case that lambda is complex and equal to I would give us that t e to the it is a solution, because this is actually d squared. Well, I'll explain this more in a future class. I don't think we have time today to do that case, but maybe next class. I just wanted to tell you the rest of the solution set is that. So then, like this problem, the solution is c1 cosine plus c2 sine plus c3 t cosine t plus c4 t sine t. I haven't quite explained why that is yet, but we're getting there. Sorry, I put the cart before the horse, but I want to erase. So, Oy. I'm trying to strike a balance between just doing theory for 2 hours and not showing you examples, but also not showing you examples out of logical order. So it's a I'm trying. Anyway, so here, that is what? That's dy dx minus lambda y equals c1 e to the lambda x. Can we solve this problem? Well, if we multiply by e to the minus lambda x, that's an integrating factor, isn't it? Reverse product rule. Integrate both sides. We get so apparently y is c1x e to the lambda x, c2 e to the lambda x. Which shows me that my d minus lambda squared y equals to 0 has y1 equal e to the lambda x, and y2 is x e to the lambda x as solutions. So this is the theorem in the case m equals to 2. All right? And my claim is that this just keeps happening. And so like we could prove that with probably mathematical induction is the nicest way to prove that. Do you guys know mathematical induction? How do we do that? Assume it's true for k, right? So suppose you got y1, k solve d minus lambda. Oh man, sorry. No, that's not what I want to say. Actually, let me decide what I want to say here. All right. Let me take a breath. Can I repeat this argument that I just made for like third order? How would that work? Let's think about it. Can we just keep doing what I just did? We have d minus lambda cubed y equals to 0. Notice e to the lambda x and x e to the lambda x solve this. It's always going to be the case that whatever solves the lower power still solves the higher power. Because if you feed it to that differential operator, it makes it go to 0, right? So at this point, I'm just going to derive and show you that it works, because I'm running out of steam here. But I do think it could be derived for higher powers. But let's look at the next one in question, x squared e to the lambda x. How's that go? So what we're looking at here is d minus lambda squared, right? Acting on the differentiation operator, acting on x squared e to the lambda x, all right? And then minus lambda times x squared e to the lambda x. Do you guys follow me here? What I'm doing? I'm still working on the proof of the theorem that I wrote on the middle board, trying to show you why past multiplication by x squared works. And I think if we do this right, you'll be able to be convinced that it's going to continue happening for higher powers. What happens when we differentiate x squared e to the lambda x? We've got a what? Nobody? So I differentiate, I get product rule. 2x e to the lambda x plus lambda x squared e to the lambda x minus lambda x squared e to, oh, look at that. Well, there's a cancellation right there, right? See that? Ooh, you're dead. Finally. So then, we already learned, though, in the previous step of the proof, that d minus lambda squared acting on this is what? Middle board, I calculated it right over there, right? D minus lambda squared y is 0 for this. We worked that out. It's right there. So this is 0, which is what we want. See, d minus lambda cubed acting on x squared e to lambda x is 0. Can we continue this calculation for like higher order? I'll do it here. Suppose we have, let's say, the kth power of d minus lambda. Well, let's say k plus 1. K plus 1th power of d minus lambda. And we're going to act on the interesting part, which is the highest order one, which would be x to the k minus 1 e to lambda x. So that's d minus lambda to the power k acting on the differentiation operator acting on x to the k minus 1 e to lambda x right? Minus lambda x to the k minus 1 e to lambda x. And what's that give us? That gives us d minus lambda to the power k. We get k minus 1 x to the power k minus 2 e to lambda x minus lambda x to the k minus 1 e to lambda x minus lambda x to the k minus 1 e to lambda x. Again, those terms cancel. Yep. Oh yeah. Thank you. Which one was positive?
I had a question for the previous part. So no matter what y ends up being, is it always going to equal 0? It's just d minus lambda squared.
What? No, for the so like for the no matter what the what?
Like, is it so? Because like what you had written down on the bell board before you erased it.
Yeah.
So, like, whatever ends up being inside those brackets, will it still equal 0, or does that part matter?
Well, d minus, I mean, this differentiation operator is only 0 on e to lambda x, x e to lambda x squared e to lambda x, and linear combinations thereof. Nothing else does it kill.
Okay. So because that's just like a variation of e to lambda x, that's why it's 0?
That is the third solution, x squared e to lambda x. So it's an example of this theorem for m equals to 3.
Yeah.
So here, these cancel, and this, you see, if we had proved the theorem up to this point, we would already know that this is 0 by like the previous step in the argument, right? So essentially, the mathematical induction, we're done. So I'll just say by induction. And if you know what that means, that's great. If you don't, it's okay. But now that we have this theorem, we can use it, right? This means we know how to write down the solution to these problems that we've started. Like today, what's the rest of this one? Lambda plus 1 cubed, right? What are my other two solutions? y2 is x e to the minus x, and y3 is x squared e to the minus x. My general solution is c1 e to the minus x plus c2 x e to the minus x plus c3 x squared e to the minus x. So we multiply by x and x squared in the instance that there's a repeat. Over here, to finish this example, I had d minus 3 squared times y. We already know that y equals e to the 3 theta is the solution. Well, y5, theta, e to the 3 theta would be the other solution. And my general solution would be c1 plus c2 theta plus c3 theta squared plus c4 e to the theta, 3 theta, plus c5 theta e to the 3 theta. And I'll explain this more next time, but basically the story is this. If we completely factor the polynomial that defines the differential equation, we simply write down the solutions, not a lick of integration to be found. After I do the integration for you in the theorem, we can just use this over and over again. This is not something you're going to rederive. This is a theorem you're going to quote and apply. All right? So this should be welcome news because I'm making good on my promise to you that differential equations is just algebra. So, but it is algebra we need to learn nonetheless. So, thanks guys.